You muted. I think you're muted.
Professor Cho, you're muted.
Okay, how's that? Wow, sorry. Think you'd get that by now. Anyway, what I was saying is welcome. I hope you had a good weekend. I hope you're looking forward to a little break here coming up for Thanksgiving. And then, wow, the end of the class comes really fast after that. So I want to just warn you, even though we do have this little break right now, there are some important things on the horizon, mostly exam 4 after we get back from Thanksgiving. We do have class this Wednesday. All right. Thanksgiving break doesn't start until after Wednesday. So we do have class this Wednesday. So make sure you come on Wednesday or watch the recorded lecture right afterwards. Right. And then this week, again, we have a written problem set. Okay. I sent you that in the weekly update email. All right. But here it is again, in case you didn't get that. That is a chapter 10B 11A problem set. All right, it'll be problems from chapters 10 and 11. And again, because you have to draw a lot of structures and everything, this is not going to be on mastering. This is just going to be on paper. All right. So I encourage you to try to do it by this Sunday night. Have it done by this Sunday night so you're on schedule for the exam next Wednesday. All right. You'll have to check your own answers on these. The answers are in the back in Appendix 3 of the ebook. And so make sure you check your answers as you go along. This problem set is a little longer than last week's, all right, simply because we've covered more material. So make sure you get on this. We'll have one more short problem set due right before the exam. And then, of course, as usual, you'll have the pretest that's due right before the exam, okay? And this week, of course, we have the normal pre and post lecture like always, all right? Yes, we're not submitting this problem set. It's not going to be on mastering. You're just going to do it on your own, and then make sure you check your answers in Appendix 3. You are responsible for all this material, right? You need to know this for the exam. Okay. All right. Before we get started, do you have any questions? No questions? Everyone doing okay? Can you? Yeah. The virus that stole the holidays, right? It's kind of a bummer. I know everyone, it's a hard time right now. Everyone having to change their plans. We changed our plans. And so it's kind of a bummer, but hope is on the horizon. That's the one good thing. So looking forward to that vaccine. All right, let's go ahead and continue on where we were before. So remember, we were talking about chemical bonding. We're still on the first of 3 bonding theories that we're going to look at. This first theory is the Lewis model. We're going to spend the most time on this bonding theory because it's the most useful at an easy level, okay? At a relatively easy level. Remember last time we talked about drawing Lewis structures, right? We learned how to do that. We talked about resonance structures. Today we're going to talk about a concept called formal charge. And I'm just going to define it here for you, and then we'll look at some examples. So formal charge is the charge an atom would have if all bonding electrons were shared equally. Okay? Formal charge is the charge an atom would have, and I should put in here, in a compound. Actually, it doesn't have to be in a compound. Never mind. Yes, it does. Yes, it does. It should be in a compound. In a compound. Formal charge, a charge an atom would have in a compound if all bonding electrons were shared equally. Okay? This is different than oxidation state, which we learned previously. Remember, oxidation state was the charge an atom would have if all bonding electrons were assigned to the more electronegative atom. That's oxidation state. Formal charge is the charge an atom would have if all bonding electrons were shared equally, right? So just to give you an example, let's say here's the Lewis structure for HF, right? If the bonding electrons were shared equally, right, then fluorine would have how many electrons in this Lewis structure? 7, right? Fluorine normally has 7 electrons, so its formal charge equals 0, right? Hydrogen, if these are shared equally, hydrogen, you assign 1 to hydrogen. Hydrogen normally has 1 valence electron, so its formal charge equals 0, right? If you remember when we talked about oxidation state, right? If you assign oxidation state here, hydrogen and fluorine have oxidation state of +1 and -1 respectively, right? That's oxidation state. For right now, though, we're going to focus on formal charge. Oxidation state helps us in deciding whether reactions are oxidation reduction reactions, right? Remember, we use them to determine what's being oxidized and what's being reduced. Formal charge helps us in drawing good Lewis structures, all right? So even though the concepts are opposite of one another, they're both useful, all right? They're both useful concepts, all right? So we're going to talk about formal charge. Formal charge, we apply it to Lewis structures, and it's going to help us decide a better Lewis structure between two competing ones, okay? So the way to calculate formal charge, the easy way to do it is just to take the number of valence electrons, which is the number of electrons that the atom would normally have, right? And the number of valence electrons, the number of electrons that it would normally have, right? And you're going to subtract out the number of non-bonding electrons, or number of, let's see how I can do this so I have room, non-bonding electrons, right? And you're going to subtract out +1/2 the number of bonding electrons. Formal charge equals, so for example, in this fluorine, right? Fluorine has how many valence electrons?
7.
7, yep. Fluorine has 7 valence electrons. So for the fluorine here, you'd have 7 minus the number of non-bonding electrons. How many non-bonding electrons here?
6.
6, right? And then plus 1/2 the number of bonding electrons. How many bonding electrons?
2.
2, right? Because those are, remember, with formal charge, you're assuming that those are equally shared between the two atoms. So that's why it's 1/2 times 2. Does that make sense? So you would find that the formal charge for that would be equal to 0, right? Okay, that's how you assign formal charge, all right? So again, what formal charge does for us is it helps us to distinguish between competing Lewis structures, and we'll apply that to Lewis structures here in just a minute. But here are some of the guidelines that go along with formal charges. So first of all, the sum of all the formal charges in a neutral molecule must be 0. So for example, in this case, they're both 0, but the sum is also 0. Okay. But for all formal charges, the sum is going to be 0 in a neutral molecule. Or if it's an ion and you assign formal charges to the ion, the sum of all the formal charges is going to be equal to the charge of the ion. Okay. Then two other rules of thumb here. You want to try to minimize formal charge. So if you're looking at 2 Lewis structures and you're trying to decide which is the best one, you can assign formal charges to all the atoms. And the one that has the least amount of formal charge is the better structure. So formal charge in a Lewis structure is something to be avoided if you can. All right. And then lastly, if you can't avoid formal charge, then any negative formal charge should be on the most electronegative atom. All right. So let's do some examples and you'll see how this works. This is just basically what we were talking about here, right? Formal charge is equal to number of valence electrons minus the number of non-bonding electrons plus 1/2 the number of bonding electrons, right? And you can sort of think about this as the number of electrons that are owned in a Lewis structure, right? Fluorine kind of owns all these 7 electrons according to the formal charge rules, okay? All right, so let's just do some examples here. We'll start with CO2. So there's a Lewis structure for CO2. And let's go through each of the atoms. Oxygen has how many valence electrons?
6.
6, right? 6 minus, right? The number of non-bonding electrons is 4, right? Plus 1/2 times the number of bonding electrons. 1, 2, 3, 4. So there's 4 of those. So it's 6 minus 4. So that's equal to 0, right? So the formal charge on oxygen is 0. Since this oxygen is exactly the same, that has a 0 formal charge as well. All right, for carbon, carbon normally has 4 valence electrons. And then we're going to subtract out the number of non-bonding, which is 0, right? Plus the number of bonding electrons. So that's 1/2 times 1, 2, 3, 4, 5, 6, 7, 8. So that's 4 minus 1/2 of 8 is 4. For 4 minus 4, that's also equal to 0. So all 3 atoms here have 0 formal charge. Okay. Sorry. Apologize. Okay, the number of non-bonding electrons are basically these guys right here, right? So you just count them up. 1, 2, 3, 4. Okay, that was the question. All right, now let's look at this one up here. S, E, F, F, and O. Right, so that's the Lewis structure here. Okay, and we can assign formal charge. Let's start with the fluorine. Fluorine has how many valence electrons?
7.
7, right? 7 minus 6. That's the number of non-bonding electrons, right? And then also 1/2 of 2 is 1, right? So that's 7 minus 7 is 0. Okay. Then this other fluorine is the same. So far we've seen all 0 formal charges. We're going to get to some here that actually have formal charge in just a minute. So selenium here, right? Selenium is right here on the periodic table. So how many valence electrons does selenium have?
6.
6, right? Minus the number of non-bonding electrons, which is 2, right? Plus 1/2 the number of bonding electrons, which is how many?
6.
6, right? So that's equal 6. So that's equal to 6 minus 3, 4, 5. That's equal to plus 1. All right. So selenium has a formal charge of plus 1. Okay. And then let's look at this oxygen up here. This oxygen up here has, oxygen normally has how many valence electrons?
6.
6, right? Minus how many non-bonding electrons?
6.
6 plus 1/2 of the bonding electrons, 1/2 of 2. So that's equal to 6 minus 7 is equal to minus 1. So this oxygen has a formal charge of -1. So notice that the sum of the formal charges is 0, as it should be for a neutral molecule, right? And notice also that oxygen is more electronegative than selenium, right? Because it's higher on the periodic table. Electronegativity goes down as you go down a column, remember, right? So that's, if you have to have formal charge, that's how you should have it. Okay. Gabby, do you have a question?
Yes, can you please do the formal charges of boron and fluorine, please? Because I tried to do it so many times and I couldn't figure it out.
It depends on the compound, Gabby. So it's different in different compounds. What compound were you thinking about a particular compound?
Yeah, boron and fluorine. Boron and fluorine, B and F.
Something like BF3.
No, it's just BF. That's all.
I don't
That's
think
what they gave us. It was in the pre-lecture.
it was just
Yeah.
it was just BF. Don't-
Yes. Yeah, that was all. Yeah, the formal charges of BF. Yeah, that's what they asked.
Right. But in what? But it's in it has to be in the compound, right? I think the compound was BF3, wasn't it?
Yeah, and it just highlighted.
Oh yeah.
It was
Yes.
BF3, but it was just talking about the BF that was double bonded. So there was a bond.
Let me
between
BF3 is a little fun. Well, we can do BF3, but
Yeah, it was BF3. I'm sorry, it was BF3.
BF3 with a double bond here, right? Isn't that
Yeah, it was
what it was?
BF3. It was yeah, double bond right there. Yes, correct. And it has
Right. So let
boron-
me get back to that, Gabby. Let me get back to that one in a little bit. Remind me in just a couple minutes, okay? I'll get to that in just a minute. All right.
Thank you.
Okay. So let's see. Where are we? We are here on NO2 minus. So let's look at that one. Here's the Lewis structure. All right. So if we look at this oxygen, right? Oxygen has 6 valence electrons. Let me show you a quick shortcut if you want to how to like count this out, because this makes it easy. You just count each bond as 1 electron, right? Because it's 1/2 times the number of bonding electrons. So each bond has 2 electrons. So you can just count each bond once, and you count each lone pair electron once, right? So you can just say, okay, oxygen has 6 valence electrons minus 1, 2, 3, 4, 5, 6, right? So that makes it easy, right? So that means it has a formal charge of 0. Nitrogen has 5 valence electrons minus 1, 2, 3, 4, 5, right? So that has a formal charge of 0. Oh, and by the way, I forgot. This is an ion with a -1 charge, okay? And then this oxygen normally has 6 minus 1, 2, 3, 4, 5, 6, 7, right? So that's -1. Okay, and again, notice the sum of all the formal charges equals the charge of the ion. Okay. Let's do, I'm not going to do all of these. Let me do, let's do this. Well, let's just do this. Let's do this one. Let's go ahead and do this one. SO32 minus. All right. Oops, and I'm missing a lone pair right here. All right, let's start with the sulfur. Sulfur normally has how many? How many valence electrons?
That's 7.
No.
6.
6,
6,
right?
I'm sorry.
6A,
Yeah.
so 6. So 6 minus 1, 2, 3, 4, 5. You see how I'm doing that? I'm just kind of counting them out. I count each valence electron, and then I count each bond as just 1, because it's 1/2 of 2, right? So it's 6 minus 1, 2, 3, 4, 5, right? So that's +1 for the sulfur. These oxygens are all the same. It's 6 minus 1, 2, 3, 4, 5, 6, 7, right? So that's -1. This is -1, and this is -1. Right? So you have a total sum of formal charges is 2 minus, like it should be for the charge of the ion, right? For charged particles, for ions, you always want to sum up to that, okay? The negative formal charge on the more electronegative atoms. So that's good. And then that's it. Okay. And
I have a
then,
question.
yeah.
So how do we know that like the atoms perfectly share like 1/2 of the bond?
That's the definition of formal charge. So for formal charge, you're basically saying, look, here's how we're assigning it. It's really just a bookkeeping method. It doesn't really correspond necessarily to reality, but it does surprisingly help you distinguish between competing Lewis structures. Okay, and I'll show you some examples of that here in a minute. Okay, so for example, formal charge can help you in deciding which might be more stable among these two isomers. Okay, so let's look at the Lewis structures for these two and assign formal charges and see if we can predict which of these two isomers is more stable. And this is a little crazy, right? That you can predict something like this from something as simple as Lewis drought structures and this arbitrary concept called formal charge, right? Because formal charge is completely arbitrary, right? We're just saying, let's just pretend that they share them equally, right? And then, but yet it works, okay? You can predict which of these two compounds is more stable. So hydrogen normally has 2 valence electrons. Sorry, normally has one assigned to it here, so formal charge of 0. Carbon normally has 4, right? Valence electrons, minus 1, 2, 3, 4. So that's 0. Nitrogen has 5. So 5 minus 1, 2, 3, 4, 5. That's 0. Okay. Here, this hydrogen is 0 again. But now nitrogen here, right? Again, nitrogen has 5 valence electrons, minus 1, 2, 3, 4. So what's the formal charge on nitrogen here?
+1.
+1, right? And then carbon normally has 4, but look, it has 1, 2, 3, 4, 5 in this structure, right? So that's a -1. So notice this doesn't have any formal charge. This does. So we would predict, based on the Lewis model, that this is more stable. We go out into the world and we look, and guess what? It is indeed more stable. And in fact, this compound, you can make it, but as it sits around, this thing flips and it turns into that because this is more stable, right? Isn't that crazy? And you can predict that with these simple little adding dots together. It's crazy that it works, but it actually works. All
I have
right?
a quick question.
Yeah.
Do all formal charges have to equal 0?
For a neutral molecule, yes. For an ion, they sum up to the charge of the ion. So here, for example, we have an ion. If you add these up, these add up to -2.
Oh, okay. I wasn't sure if you okay, that
that's
makes sense.
2 minus. Yeah, does that make sense? And
Yeah.
by the way, formal charge, just like oxidation state, you usually do the sign and then the number, whereas real charge is the number and then the sign. Okay.
Okay.
So that's how we kind of distinguish between them in terms of notation. All right. Okay, Gabby, let's look at your question. I think your question was this one. BF3, and I think
It was double bonding on top of boron.
this versus right? So if you look at this structure, let's look at this structure first. First of all, this structure doesn't have an octet on boron. Boron is one of those weird elements that oftentimes forms compounds with an incomplete octet. We'll get to that in a minute, okay? But if you look at formal charges here, fluorine normally has 7 valence electrons, 7 minus 1, 2, 3, 4, 5, 6, 7. So that's 0. These are all the same, so they're all 0. Boron normally has 3 valence electrons, minus, is family not muted? I think family is muted. That's my extra computer, by the way, so I can see what I'm doing. So where were we? Okay, so boron normally has 3 valence electrons, right? Here it is in group 3A, and it has 1, 2, 3, so it's 0. So this structure has 0 formal charge. This structure, these are 0, but now look at this fluorine. Fluorine normally has 7 minus 1, 2, 3, 4, 5, 6, right? So that's +1. Boron normally has 3, and here it has 4, so that's -1. Okay. Which of these two, now, this does not follow the octet rule, right? Which is very, very bad. You would normally not draw structures that don't follow the octet rules, except for BF, except for boron and beryllium. Those two atoms can form structures that don't follow the octet rule. We'll get to that in a minute. But this is a very, very bad Lewis structure. Why? It has a positive formal charge on a very electronegative element, right? In fact, the most electronegative element on the periodic table. So this probably is not a big contributor to BF3. Okay. Does that make sense, Gabby? Does that answer your question?
Yes, it does. Yeah.
Okay.
Thank you.
Perfect. All right. Awesome. All right. Very good. All right. Here's a question for you. Go ahead and try to answer this. I'll launch a poll.
You said from before that I'm supposed to be able to resubmit an answer before time's up, right?
I actually don't know that.
Yeah, because it doesn't. Nothing shows up here for polls.
Okay.
So,
I think you might not be able to do that. I thought maybe you could, but
okay. I mean, I don't need to do that now, but I was just
Yeah.
wondering.
yeah. I think I was wrong about that. So you're trying to get that formal charge on that nitrogen. Try to put an answer in the next 10 seconds or so. Okay, I'm gonna cut it off there, and nice work. Most of you got that. The right answer was C, -1, right? So if you look here at this nitrogen, the way you get, again, if you missed it, pay attention here. You have 5 valence electrons for nitrogen normally, minus, right? The number of bonding electrons, 1, 2, 3, 4, right? Plus 1/2 the number of bonds, so that's 4. So notice that when you do that, you count each valence electron, 5 minus 1, 2, 3, 4, and then half of these, right? So you can just count those once. So it'd be 5 minus 1, 2, 3, 4, 5, 6, right? So it's 5 minus 6 is equal to -1, right? So it has a formal charge of -1. Okay? Does that make sense?
I had a question on that.
Yes.
I did the calculations correctly and I did get -1, but do you incorporate the charge, the total charge into that where it would make it -2?
No. You calculate the formal charge of each atom individually based on the number of electrons around it, right? And then you remember that when you have an ion, the sum of all those is going to equal to the charge of the ion, right? So if I go ahead and assign formal charge to the rest of these, right? Carbon has 4 valence electrons, minus 1, 2, 3, 4 is 0, right? Sulfur has 6 valence electrons, minus 1, 2, 3, 4, 5, 6 is also 0. So notice when I sum all these, 0 plus 0 minus 1 is equal to minus 1.
Okay, thank you.
So that's where the negative charge comes in. But no, you don't take that into account when you're calculating the formal charge of the elements. Okay, so now we're going to look a little bit at some exceptions to the octet rule. I already told you a little bit about them, but there's basically 3 general types of exceptions. There's odd electron species, incomplete octets, and expanded octets. So let's go through each of those one at a time. We'll start with odd electron species. There are some molecules, like NO2, for example, okay, that have an odd number of electrons. If you have an odd number of electrons, is it possible to ever draw a Lewis structure that has an octet on every atom? It's not possible, right? It's not possible. Yet, some of these molecules exist in nature, all right? So this is a little bit of a shortcoming of the Lewis model, all right? But we need to be aware of it. So if we try to draw the Lewis structure for this, look what happens. We draw NO2, and then we add up the total number of valence electrons, right? That's 5 for the nitrogen, plus 2 times 6, that's 17 electrons, right? Again, that's an odd number, right? So you try to draw the best Lewis structure you can. You put in these electrons. That gives you 16 electrons. So far, you have one more. You put it here. That gives you 17 electrons. All right. Now, you could make this Lewis structure a little better by drawing a double bond. So the best you can do here is something that looks like this. Okay. Notice you have an octet on this oxygen, an octet on this oxygen, but this nitrogen only has how many electrons in this Lewis structure? 7. Okay, it only has 7 in this Lewis structure. It doesn't have an octet. Notice that the way that we count electrons for octets is different than the way that we count them for formal charge, right? So don't get confused. For octets, you count all the electrons, right? In terms of counting up the octet. Okay, so this has 7 electrons. So you might say, well, okay, maybe this thing doesn't exist. Well, turns out it does exist, but it actually is not very stable. Okay, it's not a really stable molecule. It's a fairly reactive molecule. All right, so it's not a total loss for the Lewis model, right? Because even though it does exist, and even though it doesn't follow the Lewis rules, right, of octets, it's not very stable, okay? So there are some odd electron species that that do exist, but generally speaking, they don't tend to be super stable, even though, and you can't draw a good Lewis structure for those. So keep that in mind. Those are odd electron species, okay? Then there's 2 elements that form compounds that have incomplete octets, okay? And those 2 elements are beryllium and boron. All right, so for example, this compound, BeH2, if you look at beryllium, right? Beryllium is right here. It has 2 electrons. So 2 for beryllium plus 2 times 1 for each of the hydrogens is 4 electrons, right? So when you draw the Lewis structure, 1, 2, 3, 4, that's it. Okay. So you might think, oh, well, this is not a very good Lewis structure because beryllium doesn't have an octet, but beryllium is one of the exceptions. Okay. Beryllium will form compounds with only 4 electrons in the Lewis structure. The second exception is boron. So you have compounds like this, for example, BH3. And this compound exists and is stable. And if we add up the number of electrons here, right, boron has 3 plus 3 times 1 is excuse me, 6. 1, 2, 3, 4, 5, 6. So that's it, right? You can't add any more electrons. Another compound is the one we just looked at, BF3, right? 3 times 7 is 21, plus 3 is 24 electrons, right? So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There's your 24 electrons. There's your Lewis structure. Again, incomplete octet on boron. All right. Now, in this case, you might say, well, why didn't I form a double bond? Right? Because if I form a double bond here, I get that. And we just saw why we can't form that double bond, right? Because boron then has a formal charge of -1 and fluorine has a formal charge of +1. Now, here's where it gets even a little more complicated. So the best Lewis structure for BF3 is the one we had before with no double bond. But remember what I said, you can often draw resonance structures, right? Resonance structures are structures where you don't change the skeletal formula at all, the way the atoms are bonded together, but you move electrons around. All right. And in this case, if you form that double bond, this is a resonance structure of BF3. Is it a very important resonance structure? In other words, is the average structure of BF3 more like this or more like this? Well, it turns out it's much more like this, right? Why? Because you have such a positive, formal charge on a very electronegative element. But the BF bond is a tiny bit shorter than what you would normally expect for a single bond between borane and fluorine, right? Which means that maybe this plays a small role in explaining the bonding of BF3, right? So resonance structures are not an all or nothing thing is what I'm trying to explain here, right? Resonance structures can be, this is the best structure, but this might play a minor role in describing the bonding. All right. So that's a little bit confusing, I know, but that's the way it is with this model that's, again, fairly simple, but is able to predict a lot of things. Questions? Are there any questions?
Wait, I got a quick question.
Yeah.
Wait, so beryllium and boron are only an exception when they're paired with hydrogen and fluorine?
No, they can form, those two elements in general tend to form compounds with incomplete octets.
Oh, okay.
Beryllium oftentimes with just 4 electrons instead of 8, and boron with 6 electrons instead of an octet.
So I guess when we're filling it out, we just fill out all the, never mind, I answered my own question.
Okay.
Thank you.
Awesome.
I have a quick question about
Sure.
the on the odd electron species. When you were doing the, I don't think you have it up there. It was one of the question about the HCN and HNC.
Oh, yeah.
I thought that we were supposed to put the least electromagnetic one in.
Yes, exactly. And remember, remember in general, it's always better to put the more electronegative elements on the end, right? And now we can see why, right? Because when you put the most electronegative elements on the end elements are the ones that tend to have more negative formal charge. And when you put the least electronegative one in the middle, that minimizes the formal charge on that.
Oh, okay.
Okay, so
Okay, got it.
assigning formal charge kind of shows you how we came about that random rule.
Okay.
Does that make sense?
Yeah, I just wasn't sure if that's
Yeah. Yeah, that was,
But I got it.
That's the reason. Yep.
okay.
Yeah, great question. Okay, so here we have this theory that has a lot of exceptions, right? It has odd electron species, it has incomplete octets, and then it also has, lo and behold, expanded octets. All right. Where can you have expanded octets? You can have expanded octets only for elements in period 3 and below. All right, elements in period 2 will never have expanded octets, only period 3 and below. Aaron, did you have a question?
I was just curious if there were any specific elements that like tend to like do the odd electron species. Like
Nitrogen is one of the big ones because nitrogen has an odd number of electrons itself, right? And let's see. But basically any element, depending on what it's paired with, can have an odd number of electrons. Again, it's not super common and they tend to be very unstable. Okay. All right, expanded octet. So let's look at some examples of expanded octets. Let's see, wait, do I have them here? No, I don't. Okay. One example of expanded octets is ASF5. So this compound, right? Arsenic is right here. It has 5 valence electrons plus 5 times 7 is 35. So that's 40, right? So if we draw the Lewis structure for this, fluorine, 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 fluorine. We give all of the fluorines octets. Right, and that's 8 times 5 is 40 electrons, right? So we've used up all the electrons. Notice though that arsenic here has a expanded octet, right? It has 10 electrons around it, okay? That's okay as long as it's period 3 or below, right? And since arsenic is right here, it's period 3 or below, so it's okay for it to have an expanded octet. All right. Another example is SF6. One, two, three, four, five, 6. So the number of electrons here is 6 for the sulfur, plus 7 times 6 is 40. 6 times 7 is 42, and 6 is 48, right? So 48 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I'll just put them all in. Right, we got 6 times 8 is 48, right? So we've used all of these electrons. Sulfur, notice, has 12 electrons around it. Expanded octet of 12. Again, sulfur is period 3 or below, so that's okay. Never ever expand the octet on period 2 elements. Never allowed. Okay. However, if you have a period 3 element or below that has a formal charge, you can expand the octet to lower the formal charge. So for example, remember this guy that we did earlier? It had a formal charge of +1 on the selenium and -1 on the oxygen, right? Notice what happens if I move an electron pair down to there, then I get this structure. Now, look at the formal charge on the selenium. Now it's 0. Formal charge on the oxygen is 0. So by moving that electron here, expanding the octet on the selenium, I lowered formal charge. Okay? So you can expand octets to lower formal charge on period 3 or below elements, but never on period 1 or 2 elements. Okay? Never expand the octet on those elements. All right, here's another example, SO32-. So remember we drew this Lewis structure. The formal charge was +1, -1, -1, -1. Look what happens if I create a double bond by moving electrons from here to here, right? That structure would be this. Now, this sulfur, right, normally has 5 valence electrons. How many assigned to it here? 1, 2, 3, 4, 5, 6. So that's -1. No, wait, is that right? No. 1, 2, 3, 4, 5, 6, right? So 6 minus 6 is 0. So it has 0 formal charge. This oxygen has 0 formal charge. And these oxygens each have -1 formal charge. but you went from all of this formal charge, you've reduced the formal charge, right, by expanding that octet on the sulfur. Is that a good thing? Yes, because that is a period 3 element or below. Okay, so you can expand octets in order to lower formal charge, but only on period 3 elements or below. All right, go ahead and try this one yourself.
Wait, Joe, can you re-explain how the structures on the right, the Lewis structures on the right, the ones that you have written on pen?
Yeah.
So I guess so I like left for a bit, and I just don't understand how there could be, I guess, more than 4.
Right. So
On
what
each
I said was for period 3 or below,
Mhm.
elements that are in period 3 or below, you can have what are called expanded octets. And expanded octets could be 10 or 12 electrons instead of 8.
10 or 12 electrons.
Right. So again, it's just kind of a modification to the Lewis model, right? And it's because the Lewis model is a little overly simplistic.
Mhm.
And these things occur and they're stable. So in these kinds of elements, you could have what are called expanded octets, which are 10 or 12 electrons instead of just 8.
Okay, and you do that only when they're all the same element, or can you?
You do that only when it's period 3 or below. So only in elements like these here mostly, not these.
No, no. What I'm saying is, okay, so like the AS or S, those are the ones that you can expand to 10 or 12. But when do you know that you can do it up to 10 or 12? So it's like,
So anytime, when you draw structures like this, and like the one that I'm asking here, has an expanded octet as well. So
Mhm.
you'll see when you draw this structure that you're gonna have extra electrons, so you're gonna have to expand the octet on the xenon.
okay, got it. Thank you.
Yeah. All right. I'm seeing a little bit of struggle here with this one. So let's do it together. So xenon F2, right? So you'll start out, you'll say, okay, how many valence electrons in xenon? 8. Fluorine, 2 times 7, right? So you got 14. And 8 is 22, right? 22 electrons. So then, of course, xenon is going to go in the middle because it's the least electronegative. You're going to put the fluorines on the end like that, right? And then you're going to put in the lone pairs on the terminal atoms. And so far, if you count this up, we've used 8 and 8, that's 16, right? 16, I still have 6 more electrons, right? So what am I going to do with them? I can't add them to the fluorine. That already has an octet. I can't expand the octet on the fluorine, But xenon, it's period 3 or below, so I can expand the octet on the xenon, right? So I put in the extra electrons on the xenon, and my Lewis structure looks like that, right? So how many lone pair of electrons on the xenon?
3.
3, right? So the best answer is C3. Okay? Does that make sense? And that's again an expanded octet. So a lot of you got C, but a lot of you got B as well. So you thought there was 2, but you can't, you have to use all 22 electrons, right? You can't stop. Right? So you have to, if you didn't put in this, if I didn't put in this last pair here, right? Then I'd only have used 20 of them, right? And you can't do that. So that's why B can't be correct.
And why can we put them as double bonds with the fluorine?
Oh, why? Oh, you can't. Another great question. Why can't you do double bonds with the fluorine? Okay, let's try that. So instead of putting that electron pair there, let's do this. So now look what happens. That's even worse, right? Because now you have an expanded octet on the xenon, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is okay. But you also have an expanded octet on the fluorine, and that's a big no-no, right? Never, never, never have expanded octets on period 2 elements, right? No expanded octets on fluorine ever, ever, ever. Does that answer your question, Javier?
Yes, thank you.
Yeah. Okay, very
I have a
good.
question towards
Yeah.
the expanded. If they weren't in period 2, and let's say we have another, let's say we're chlorine, would we be able to do a double bond there, or would that still be wrong?
You would still end up with a positive formal charge on the fluorine, which is not great. Sorry, on the chlorine. So it'd be better to, if you had a period 3 element in the middle, it'd be better to expand the octet on the period 3 element, period 3 or below.
Okay.
Okay. Good question. All right. Our last topic of this chapter is bond energies and bond lengths. All right. So we've seen a lot of chemical bonds in our Lewis structures. And I see a question here real quick. Alex?
Yeah, I was wondering why when you did the Lewis structure for the xenon F2, why you didn't put double bond or more than a single bond between.
I just explained that, right?
Oh, you did? Okay, sorry.
Because that would expand the octet on the fluorine.
Oh, okay, okay.
And you can't expand the octet on the fluorine. And not only that, but that would put a positive formal charge on the fluorine as well, which is even worse.
Okay, sorry.
Yeah. Okay. Good. All right, let's look at bond energy. So bond energies is, the bond energy is just the energy required to break a chemical bond. Right? And that is always, always, always endothermic. It always takes energy to break a chemical bond. Breaking a chemical bond never gives off energy. Now, this can be very confusing when you take biology, because biologists talk about storing energy in chemical bonds as if you can store energy in a chemical bond and then you break the bond and the energy comes back. That is not true. Okay? We'll see what they mean by storing energy in chemical bonds in a minute, but chemical bonds, write this big in your notes, always take energy to break a chemical bond. It's always, always, always endothermic. It's always a positive quantity. Okay? So for example, to break the chlorine-chlorine bond takes 243 kilojoules of energy. To break the hydrogen-chlorine bond takes 431 kilojoules of energy. So we say that this bond is stronger than that one, right? Why is it stronger? It takes more energy to break it. A nitrogen-nitrogen bond takes 946 kilojoules of energy. That's a really strong bond. Remember the Lewis structure for nitrogen? It has a triple bond, and triple bonds are generally stronger than double bonds, which are generally stronger than single bonds. Okay. Now, what we find is that the same kind of bond can have slightly different bond energies in different compounds, right? So for example, the CH bond in methane takes 438 kilojoules to break. In CF3H, right? So you replace those hydrogens with fluorines, and now it's a little stronger, 446 kilojoules, right? If you have bromines instead, it's a little weaker, right? But it doesn't vary by too much, all right? So what we can do is come up with a table of average bond energies, which is the average value of that bond in a lot of different compounds. So for example, the CH bond here, you notice the range. If we look at the CH bond here, it's 414 kilojoules, right? That means on average, it takes that much energy to break a CH bond, all right? Notice the ranges here, you know, the very strongest bonds are like 1,000 kilojoules per mole to break, right? The very weakest ones are like in the hundreds, okay? Another trend you see here is that look at nitrogen, 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 single bond, double bond, triple bond. What do you notice? What do you notice in the trend for bond strengths here?
The energy
Requires more energy.
Yeah, a triple bond tends to be stronger than a double bond, tends to be stronger than a single bond. See it again here with carbon. Look at that. 347, 611, 837. Right? As you go from single to double to triple, the bonds get stronger. Okay? It takes more energy to break a triple bond than it does to break a double bond. Let me see something here. Bond lengths, as you go from triple to double to single, again, they get weaker in this direction, triple to double to single, but they also get longer. So another thing to remember is that a triple bond tends to be shorter than a double bond, which is shorter than a single bond, right? So as the bond gets stronger, it also has this tendency to get shorter, okay? So keep that in mind as well. Okay. Now, the very nice thing about these average bond energies is that you can use these to figure out delta H for reaction. So remember when we were talking about thermochemistry, you guys learned how to figure out delta H for reactions. And one of the most universal ways was to use those tables of tabulated standard energies of enthalpies of formation, right? And we did the enthalpies of formation of the products times their stoichiometric coefficients minus the enthalpies of formation of the reactants times their stoichiometric coefficients, right? Here's yet another way to estimate delta H for reactions. You can basically just say, okay, how much energy does it take to break the bonds that are broken in the reaction? And then how much energy do you get back when you form them, right? So delta H for a reaction is equal to the sum of the delta H's for the bonds broken. And those are always going to be positive, right? Plus the sum of the delta H's for the bonds formed. And those are always going to be negative. Again, breaking a bond, always endothermic. Forming a bond, always exothermic. Forming positive, breaking positive, forming negative. Okay? Think about it this way. If two atoms are attached, what do you have to do to tear them apart? You got to put energy in, right? So that's always endothermic. When they reattach, energy comes out again. Okay, so that's how you can remember this. So let's say, for example, we wanted to figure out the change in enthalpy that occurs when this reaction happens. Okay, so what we can do is just say, okay, well, what are the bonds that were broken? And what are the bonds that are formed? and then add up those values according to this equation, we get delta H reaction, right? So what are you breaking here? Well, a lot of times you have to draw the Lewis structures in order to clearly see what bonds are being broken and what bonds are being formed. Okay, so there are the Lewis structures. I'm not going to put in all the extra electrons, but you can see, right, that in order to have this happen, I got to break a CH bond. I got to break a CCl bond, right? And then I get to form this bond, and I get to form that bond, right? These other bonds don't do anything in the reaction, right? So what I can do is I can say, okay, delta H for the reaction is going to be equal to a CH bond. So I look that up in the table. CH bond, 414, right? Sorry, I want to do it like this. I want to set it up. So I want to say bonds broken. I'm going to add them together here. So bonds broken, bonds formed. All right. And then I'll sum them in a minute. So bonds broken is I'm going to break a CH bond. I looked that up. That's plus 414 kilojoules, right? And then I'm going to break a CCl bond. Look that up in the table. Let's see, where is it? There it is, 243, right? And then I'm going to form a CCl bond, right? Look that up in the table, 339. But now, is that positive or negative?
Negative.
That's negative, right? So I'm going to put that negative sign there. And then I'm going to form an HCl, right? And HCl, if I look that up, is right there, 431. And again, negative. Okay? So how much energy does it take to break all the bonds that I'm breaking in this reaction? That's equal to 657 kilojoules, right? And how much energy do I get back when I form them? Minus 770 kilojoules, right? So delta H is equal to this plus this, right? So that's equal to negative 113 kilojoules, right? So overall, is the reaction endothermic or exothermic?
Exothermic.
Exothermic, right? Because it's negative, okay? But notice I can calculate it just from looking at the bonds formed and the bonds broken. So when biologists say that energy is stored in chemical bonds, that's really not correct. A better way to say that is if you take strong bonds and form weak ones, right? That takes energy, right? So if you break strong and form weak, that takes energy. If you break weak and form strong, that gives off energy, right? So what happens in respiration, right, where you're storing energy in chemical bonds, really what you're doing is you're breaking strong bonds and forming weak ones, which can later then react to reform those strong ones, giving off energy. All right. That's the much better way to think about it than to think about energy being stored in chemical bonds. Chemical bonds, always, when you break a chemical bond, you always have to put in energy to do that. Okay. So the only way you get energy out of chemical bonds is by breaking weak ones and forming stronger ones. And then you get exothermic processes. Okay. Let's do another example.
Does this mean that our reactants are always positive?
Say that again.
Our reactants are always positive and our products are going to be negative?
I don't want you to think of it that way. I want you to think about it as breaking bonds is always positive. Forming bonds is always negative.
Okay.
Now, it is true that typically you're going to break bonds in the reactants and form them in the products, but I don't want you to think about reactants and products that way. I want you to think about bonds. Breaking bonds positive, forming bonds negative.
Okay.
All right, so let's try this one. Bonds broken. Bonds formed. So in this reaction, what are you breaking?
The hydrogen bond.
HH bond, right? So HH bond is 436. So 436, that's positive. What else are you breaking?
A double bond between oxygen.
Double bond oxygen, which is right here, 498. So plus 498, right? So you're going to sum those up. And that's going to be plus 934 kilojoules. Now we'll go here. What bonds are you forming here?
Single bond between hydrogen and oxygen.
Right? Single oxygen hydrogen bond, which is right here. And how many of those are you forming?
2.
2 times plus 464, right? And then what else are you forming?
A single bond between oxygen, which is
Ex-
142.
Exactly right. Oops, and what did I do wrong?
Supposed to be
Then you
negative.
have to be negative.
That should not be positive. That should be negative. Okay. And then the oxygen bond is also going to be negative, and it's going to be negative 142, right? So when I sum those sides up, I get minus 1070, right? So delta H is equal to 934 minus 1070, and that's equal to minus 136 kilojoules, right? So again, we have a net exothermic reaction. Okay? All right, I want you guys to try this one. All right, go ahead and try that one. Be a little bit careful here when you're doing this CO2. Notice that a C double bond O is 736, but there's little asterisks by it. CO2 is so far out of the norm that they just have it has a different value. Okay, so the C double bond O in CO2 is 799 kilojoules, not 736.
Is the coefficient included in the calculations?
Well, remember, you got to account for each bond broken, right? So how many oxygen double bonds do you have to break here?
2?
2, correct.
Okay.
And how many OH bonds are you forming over here?
4?
Yep, correct. So the answer is yes, you have to account for these coefficients when you add up the number of bonds broken and formed. Okay, I know some of you are still working on this. Try to finish it up in the next 15 or 20 seconds or so, and then I'll go through it real quick. So we're running out of time. Okay, 5 more seconds. All right, so most of you that finished were able to get the right answer. A few of you got a different answer. So let's just go through this really quick. What you have here is you got to add up the bonds broken and the bonds formed, but it's a little more complicated than the ones we did, right? So how many CH bonds do you have to break to get from here to here?
4.
4, right? So it's 4 CH bonds, right? And each CH bond is 414 plus 414, right? But you got to multiply that by 4. Okay. And then how many O double bond O bonds do you have to break?
2.
2, right? So it's 2 times the OO bond, which is right here, 498. So 2 OO bonds is 298. This is times 4. This is going to be times 2, right? And that's positive as well. So if you add all that up, you got to put in 2,652 kilojoules to break all the necessary bonds, right? How much energy do you get back when the new bonds form? Well, how many CO bonds are you forming? C double bond O.
Isn't the O double bond supposed to be 498, not 298?
What did I do here? 498. Thank you. Sorry, that is 498. You're correct. 498. I think this number is correct. I just wrote down the wrong number there. It's 498. Oxygen, 498. Yeah, thank you. How many CO bonds are you forming?
2.
2.
2, right? 2. So that's going to be, and then remember, this is in CO2. It's a bit of a small thing down here, but it's important to notice that. So that's 799 times 2, right? For the CO2. And then how many OH bonds are you forming?
4.
4. So that's 4 OH. OH is right. Where's OH? It's right here, 464, right? So that's, and this is negative, right? minus 464 times how many? 4, right? So when you add up all that, you get negative 3,454, right? So delta H is equal to plus 2652 minus 3454, and that's equal to minus 802 kilojoules. Does that make sense?
I have a quick question.
Yeah.
So why were we using 799 again instead of 736?
Because 736 is the average COO bond length, but CO2 is such an outlier. So remember how I said these were average and that they can vary a little bit, right? CO2 is such an outlier that they just have a separate value for CO2 in the table because it's so far away from what the average is. Okay, so any other CO bonds that you see would be 736, but when you see CO2, that's 799.
Okay.
Okay. All right, so the right answer is B, 802. And again, a lot of you got that, but that's how you do it. Does that make sense? Any questions, any other questions on this?
I have a question.
Yeah.
So we multiplied the CO2, the negative 799 by 2.
Yes.
But isn't that just one CO2?
No. It's two bonds. It's one CO2, but every bond energy is specific to one bond and one bond only. So how many CO bonds are there in here? There are 2 bonds.
Right.
So that's why you got to multiply it by 2.
Okay.
Great question. Any other questions? Okay. The only other thing is the bond lengths that we talked about briefly, right? So the bond length is just the distance between the bonded atoms, all right? And you can see as atoms get bigger, the bond lengths get bigger, right? As you go from triple to single to double to single bond, the bonds tend to get longer as you go towards less bonds, shorter as you get to more bonds, right? Typically, as a bond gets shorter, it also gets stronger, but that's not always the case, as you can see here. Or another way to think about it is a bond gets longer, it tends to get weaker, but that's not a perfect correlation because there's lots of exceptions to that. All right. But there's a table in your book too that has average bond lengths. Again, you can see in going from single to double to triple, what happens? The bond gets shorter, and we already know that it gets stronger, right? Okay. That's it for chapter 10. So we finished chapter 10. We'll start chapter 11 on Wednesday. All right. Make sure you keep up. Now, I know we have this little break here, but we have a test coming up pretty soon. So you don't want to fall behind right now. We're so close to the end. You guys have been doing a great job. Give it this last little boost and you're going to do well in this class. Okay. Don't let it slide. Stay with it. Thank you all for your attention. I'll stick around for questions, but otherwise you're free to go. Have a great afternoon.
Thank you.